Hello students, welcome to today's lecture on theory of machines. In continuation with the topic of brakes, let us today discuss the analysis of band brakes. In previous lectures, we have already discussed about the band brake and its classification. We learned that band brake consists of a belt and a flexible steel band lined with friction material which is pressed against the external surface of a cylindrical drum when the brake is applied. The force is applied at the free end of the lever. We also learned that band brake are of three types: simple band brake, differential band brake and bend and block brake. So in today's lecture, we will discuss about the simple band brake and try to derive equations needed for its analysis. Let's first understand the construction details of band brake and its working. So as you can see here, this is the drum around which this belt or the bend is wound. One end of this bend is fixed to the lever, then this lever is hinged at this point. The other end is fixed to the lever again. Now as the drum is rotating, in order to stop this drum, the force will be applied in this direction as shown here on the lever, so that the belt is pressed against the drum and the drum stops. Let's see how does it work. You can see the drum is rotating and this force is applied. So the belt is pressed against the drum and the drum is stopped, and hence the brake is applied. We'll see once again. So this is how the brake is applied. Now let's see the line diagram and see the forces involved in it. So this is the drum which is rotating in a clockwise direction. This is the lever which is hinged at this place. One end of the belt is attached to this hinged position and other end of the belt is fixed here on the lever. The distance between the fulcrum point and the other end of the belt is A, and the distance between the fulcrum point and the point at which the force is applied on the lever is L. That is nothing but the length of the lever. You can see this, that the belt is wrapped around this drum in this portion, and the angle subtended by this portion is nothing but theta, and this is known as angle of wrap or angle of contact. The radius of the drum is R. So these are the construction details, and suppose now this force P is applied, so this portion will be moved in the upper direction, in this direction as shown. So this will get tightened. So we have this as the tight side and this as the slack side. You can see there will be tension in this belt T1. This will be the tight side, and there will be tension in this belt also T2, which will be less than this T1. So it will be the slack side. As the drum is rotating in the clockwise direction and we are pulling the belt in this upward direction, so there will be a tension developed in this portion of the belt, and this portion will be the tight side, and this portion will be the slack side. Now let us try to understand the concept of this tension, how this becomes tight side and this is the slack side, and why this tension T1 is more than this tension T2. For this, let's visit the topic of belt and pulleys, which you might have learned in the subject of mechanics, maybe in your first year. So let's revisit it and try to understand the concept. To transmit torque from one shaft to another effectively, it is necessary that the belt does not slip over the pulley. To understand the action of belts on pulley, consider a belt resting on the rim of a pulley, as shown here. The belt is wrapped around the pulley to subtend an angle theta at the center. The belt is tightened on the pulley by applying an equal amount of pull on the two ends of the belt. This results in an initial tension T on each end of the belt, as shown here. Now if a small torque or tangential force F in the clockwise direction is applied to the driving pulley, it tends to rotate the belt with it, as shown here. But if the motion of belt is resisted, the pulley will have a tendency to slip over the belt. Let's see the effect of tangential force applied by considering the equilibrium of pulley and belt separately. So let's draw the free body diagram separately. Now, considering the equilibrium of pulley, it can be said that slipping of pulley is prevented by a frictional force Fp acting in the counterclockwise direction. as shown here. This is the force F that is applied to rotate the drum. So a friction force in the counterclockwise direction will be developed, that is Fp, and this Fp will be equal to F as per the equilibrium condition. Direction of frictional force will be anti-clockwise because the drum is rotating in the clockwise direction, so the velocity of the drum at this point will be in this direction. Similarly, considering the equilibrium of the belt, it can be said that belt will be prevented from slipping in the counterclockwise direction, that is opposite to that of pulley, due to frictional force Fb equal to F in the clockwise direction, opposite to that of pulley. So there will be a equal and opposite frictional force developed in the belt as shown here. So Fb will be in the clockwise direction and Fb will be equal to Fp, and both of these will be equal to the force F applied according to the equilibrium condition. The frictional force in the belt results in increased tension on one end of the belt T1 and a decrease in tension on the other end T2, such that by the equilibrium of forces in the belt we can write that T1 will be equal to T2 plus F, as T1 is in this direction and F and T2 are in this direction. Fb and T2 are in opposite direction. So T1 will be equal to Fb plus T2 as seen from the diagram. So this is nothing but we will get that F will be equal to T1 minus T2. If the tangential force on the pulley is increased, at one stage it will just cause relative motion, that is slip, between the belt and the pulley. This will indicate that the frictional force has reached the limiting value and the force F on the pulley should not be increased further. Now consider a belt and pulley arrangement as shown in figure. Here a belt with an initial tension T passes over the driving and the driven pulley. This is the driving pulley and this is the driven pulley. On the driving side, the belt would rotate with the pulley with no relative slip between the two as long as the tangential force on the pulley F, which is equal to T1 minus T2, is less than the frictional force as we discussed earlier. On the driven shaft, the pulley rotates with the belt in the clockwise direction, which means that pulley can have a tendency to slip back in the counterclockwise direction. This implies that the belt will have tendency to slip over the pulley in the clockwise direction, meaning a counterclockwise frictional force equal to T1 minus T2. So on the driven side, the counterclockwise frictional force will be acting, that it will be equal to T1 minus T2. Thus we say that in clockwise rotation, tension T1 will be more and tension T2 will be less, and thus this lower portion will be the tight side with higher tension T1 and the upper portion of the belt will be the slack side with lower tension T2. So this is how we understand that how due to the rotation of the drum, one of the sides has higher tension and other side of the belt has lower tension. So we'll consider T1 as the higher tension and T2 as the lower tension. And the side with higher tension will be the tight side and the side with lower tension is known as slack side. Moving ahead, let us now derive the equation of ratio of friction tensions, which we will be using in the band brake analysis. This equation you might have learned again in your engineering mechanics subject. For those who have not, let us derive this equation. Consider a pulley as shown in figure. In this figure, T1 is tension on tight side, T2 is tension on slack side, theta is the angle of wrap, mu is the friction lining coefficient. Now consider a short length of the belt subtending an angle del theta at the center of the pulley as shown. So this is the small element that we have considered, and we'll just try to find out the tensions here and then we'll integrate to obtain the ratio of the tension. Here there will be a normal reaction on the belt by the drum. N is the normal reaction on this element. T is the tension on this side. This will be the slack side as the drum will be rotating in the clockwise direction, and T plus delta T is the tension on the tight side. Delta T is the increase in tension on the tight side than that of the slack side. Tension T and T plus delta T act in the directions perpendicular to the radii drawn at the ends of the elements as shown here. This is perpendicular to this radii, this is perpendicular to this radii. The friction force mu n will act tangentially to the pulley rim, resisting the slipping of the elementary belt on the pulley. This is the direction of mu n, as the drum will be rotating in the clockwise direction. This angle will be delta theta by 2 as per the geometry, and this angle will also be delta theta by 2 as per the geometry. Now resolving the forces in the tangential direction, that means in this direction. So we have mu n plus t into cos delta theta by 2. T will be resolved in this direction as cos t into cos delta theta by 2, and this will be resolved in this direction, in the opposite direction, as t plus delta t into cos delta theta by 2. So the equation will be mu n plus t cos delta theta by 2 minus t plus delta t cos delta theta by 2 will be equal to 0. Now as the delta theta is very small, so cos delta theta by 2 will be nearly equal to 1. So putting this value in this equation, we get mu n t, this will be 1, and t minus t and minus delta t, and this will be again 1, will be equal to 0. So this will give us delta t is nothing but mu n. So we consider this as equation number 1. Now resolving in the radial direction, that means in this perpendicular direction. So in this direction we have n is in the upward direction, then t sine theta by 2 will be in the downward direction, and t plus delta t sine theta by 2 will be in the downward direction. So the equation will be n minus t sine theta by 2 minus t plus del t sine theta by 2 is equal to 0. Now as del theta is small, so sine del theta by 2 will become nearly equal to del theta by 2. So this will become del theta by 2, and this will also become del theta by 2. So this will give n minus t del theta by 2 minus t del theta by 2 t into del theta by 2. So now neglecting the product of small quantities. So del t into del theta will be the small quantities. So neglecting the product of del t and del theta, we will have minus t del theta by 2 and minus t del theta by 2 from here. So this will both add up and give us t del theta. So we will have finally n will be equal to t del theta. Now inserting this value of n in this equation 1, we get del t is equal to mu into t del theta, which can be rewritten as del t upon t is equal to mu del theta. Integration of del t upon t, integration of dt upon t from t2 to t1 will be equal to 0 to theta mu d theta. So after integration we have log of t1 upon t2 will be equal to mu theta. This is the log base e. So this can be written as t1 by t2 is equal to e to the power of mu theta. So this is the ratio of the tensions. This equation we will be using very frequently in the analysis of band breaks. I should also mention here that if the rotation is counterclockwise, then this side will be the tight side, T1 will be here, and this side will be the slack side, that is T2 will be here. So this is all for today's lecture. We will proceed with the analysis of simple band break in the next class. I hope you have understood the concept of tight side and slack side, why the tension T1 is more than the tension T2. In case of any doubt, please feel free to contact me. Thank you.